Okay, so as I said, we are starting kind of the HL level of periodicity. So for SL, it was topic 3. And so what happens when we do the HL stuff is to kind of extend it but relate it, they put a 1 in the front. So this stuff is all technically referred to as topic 13. So if you hear me say topic 3/13, this is what I'm talking about the SL and the HL level material. So we're going to do the first part today. And so I'm going to go down here so we can look at kind of the little summary at the beginning. All of the HL level material focuses on transition elements. And so you can see obviously here it says we're doing first row D block elements. And so the D block is that first row of transition elements from scandium to zinc. And so we're going to be focusing on specifically that row and those elements and sort of some of the trends, some of the properties, physical and chemical properties that they have. And we're going to look at kind of their electron configurations and to kind of explain why they have certain properties and things like that. And then specifically, these elements form these kind of weird, complex ions and things like that. So we're going to start talking about that today, and then we're going to continue talking about it next week as well. So here under the understandings for today, we're going to start talking about the variable oxidation states. Next week, we actually get more into detail about how to like calculate and figure that out. We're going to talk a kind of an intro today about how they form, as I mentioned, complex ions with this thing called ligands, or a ligand is just a singular one. And so we're going to talk about kind of an intro to that today. The other things in this first bullet we're not going to get to until later next week. So we will talk about how some of the compounds that they form are going to have different colors, and we're going to talk about some of their properties that are like catalytic and magnetic properties. The second bullet, we will cover this today. We will talk about why zinc is technically not considered to be a transition element, even though it is in the third row D block. And we'll start talking about the oxidation states more next week, I believe. I think we kind of touch on the beginning of it today, but we're not going to get into more detail about it until next week. Okay. For applications and skills, a lot of these let's see, I'm trying to think. So this first one, we're going to talk about this one today. The deduction of the charge, that won't be until next week. The magnetic properties will be next week. And then we'll talk sort of an intro about how they have multiple or variable oxidation states today, but we won't get into more detail about explaining it until next week. Okay. And then just know that, like with our other topics, there is some information in the data booklet that you can refer to if you need help on answering certain questions. So it says common oxidation number of the transition metal ions. They're listed in the data booklet in sections 9 and 14. So if you need to look up the oxidation numbers, which is kind of the charges of the transition metal, since they have multiple possible charges, that's where you would look and refer to that information. All right, so this is kind of your checklist where you can kind of keep track of what we're going over. So we're going to do this first one today. We'll talk about how we define something as being a transition element. We'll talk about the structure and the bonding in a complex ion. We'll talk about coordination number and the geometry. And I believe that's where we are stopping today, because we're not going to be talking about determining charges and some of these properties and things until more next week. Okay. All right. So beginning here is kind of just a basic intro, like what is a transition element? Like how do we actually define it? Because usually, in kind of intro beginner chemistry, like you guys did last year, we really just say, oh, well, a transition element or a transition metal, oh, it's something in groups 3 through 12 on the periodic table. And we say, well, it's in that D block. Those are transition metals. But we don't really talk about why that is. And so here, this is like our actual definition. So a transition element has to be an element whose atom has an incomplete D sublevel, or it can form a positive ion with an incomplete D sublevel. And so what that means is we're going to have to look at the electron configuration or the orbital diagram to determine if something would fit that definition. Because if it's incomplete, that means that it will not have 10 electrons. Because remember, the D sublevel can hold up to 10 electrons in it, 5 pairs. because D has 5 orbitals. And so if it has 10 as either a neutral atom or as an ion, positive ion, then it would not fit that definition. Okay, so all of these are the elements that are in that first row on the D block, okay, from scandium to zinc. But here is where that definition kind of comes into play, because technically zinc is a D block element because it's on that row in the D block, but technically by this definition, it is not a transition element. And the reason is that we're going to talk about it in just a minute, because we're going to look at the electron configuration. But basically, it's because when zinc is a neutral atom, excuse me, and an ion, it has 10, its D sublevel is completely full. Okay, it's not incomplete. And so that makes it not follow that definition on that first bullet. So technically, we cannot call it a transition element according to our definition that we have here. And so that's kind of what it's summarized in that second bullet, is that it doesn't have an incomplete D sublevel as an atom or an ion. And so if we look at the electron configurations of all of these elements in the first row on the D block, we can see that except for zinc, all of them have an incomplete D sublevel as either an element or as an ion, or both. Okay. So for example, here, scandium as an atom, or as a neutral atom, it's 3D1. Titanium's 3D2. We got 3D3, 3D, and then we got chromium's 3D5 because it's that exception, so it kind of skips the 3D4. It's 4S1, 3D5. Manganese 3D5, 6, 7, 8. And then copper, it has 10, so it has a complete D sublevel as an atom, but over here as an ion, it does not. Okay. And so all these other ones, they have incomplete D sublevels as both an atom and an ion. Copper only has an incomplete D sublevel as an ion. And then scandium only has an incomplete D sublevel as a atom. Because up here, when scandium becomes an ion, it's got a +3 charge. So that means it loses both of these electrons in the S, and it loses this one in the D. So it goes back down to the next level. And so its configuration changes to this. And so it doesn't have an incomplete D sublevel, because now it doesn't even have a D sublevel, but it had an incomplete D sublevel as an atom. So scandium has it as an atom, copper has it as an ion. The rest of them all have incomplete D sublevels as both an atom and an ion. Okay. The only one that doesn't have incomplete as either a atom or an element is zinc. Both of them end in 3D10. And the reason for that is because if I look here, zinc forms a +2 charged ion, and they're all of these elements, they're always going to lose their S electrons first, because the S electrons are in the 4th energy level, and that's higher than 3D. Okay, they're further away from the nucleus because they're in the 4th level. So it will lose the 4s2 electrons, and that's why it turns into just Ar3D10. So it still has a complete D sublevel. So that is why zinc is not considered a transition element by our definition, because both as an atom and as a positive ion, it has a complete D sublevel. Okay. And that's basically what these bullets down here are kind of summarizing. So it says that, scandium to copper, they have either an atom or a positive ion. So one or both. Zinc is only included to show its configuration so that you guys can see that it does not have an incomplete D sublevel as an atom or an ion. And so because of that, we cannot label it as a transition element according to our definition. Okay. So you have some practice questions there. I'm going to go down here. So the next section talks about some physical and chemical properties of the transition elements. Okay, so these are all the ones that are in the D block that fit that definition that we just talked about. So these are all metals. Okay, in this area of the periodic table, they all lose electrons. But these are the metals that a lot of times we think of when we think of the word metal. Like if I told a younger kid, well, what's an example of a metal? They might say something like gold, copper. Okay, those are kind of the common metals that we think of when we hear the word metal. Okay, and that's because they're used in a lot of different ways in life. We use like gold, silver, platinum. Those are used to make like jewelry and things like that. Copper is used in wiring and housing because it conducts electricity very well. Titanium, what was I thinking of? Not titanium. Chromium is used in things. Cobalt is used in things. Zinc is used like, so all of these elements that are in this section of the table, they're common because they don't have high reactivity like the alkali metals and alkaline earth metals. They do still have reactions, but a lot of them are not as reactive as the alkali and metals and alkaline earth metals. And so because of that, and then all of these other properties they have, that makes them very useful in everyday life. We can use them to build materials because a lot of times they're very strong. We can use them to make jewelry and to make objects for houses because they're very malleable and ductile, and we can shape them however we want to shape them. A lot of them conduct electricity and heat. So, we use them to cook things. We use them to, for wiring in houses. We use them for pipes, for plumbing. Okay. So that's kind of what it's summarizing on here. So they have high electrical and thermal conductivity. So as I mentioned, like copper wire is in every building, every house, every apartment, every, school, business, whatever. Inside the walls, when they are building things, there's copper electrical wire running because that's what conducts electricity the best. And so that's typically what they use and things like that. They also have thermal conductivity. And so thermal conductivity, so you can use things for like pots and pans. Okay, all of like our stuff we cook with, they're all made of metals because they conduct electricity very, very well. So there are some people that have like copper pots. There are some that aren't pure elements. They're more alloys, like steel is an alloy. But if you have like iron, like I have cast iron pans at home that was like they were my grandma's pans because they're really old, but they're very durable and they conduct heat really well. And so they're really good for cooking because of that. They have high melting points. So that means that you can heat them up. So again, they're good to use for things like heating and cooking things because they can withstand high heats without melting some of them. They're malleable, so we can beat them or shape them however we want. We can flatten them out, we can shape them, bend them and shape them a certain way. So that's very useful because we can make them whatever shape we want. You can make it into a ring to fit around your finger. You could make it into a pot or pan to cook in. You can, shape it into a pipe that you can put in your house to, carry water to your sinks and things like that. So because you can shape and mold them, that also makes them very useful because they can be shaped into whatever we want. High tensile strength. So this means that they can withstand a lot of force. And so this is what makes them good for building things. So I'm just going to put here, they can withstand high force or high weight. And so that's why a lot of times you'll see metals used in building things because they can, withstand such high forces or such high weights and things like that, and they can still, they might bend a little, but they don't break like certain things because they're not brittle. They are ductile. So ductile is kind of similar to malleable. It has to do with shaping, but specifically ductile means that it can be drawn into a wire. So that goes with kind of up here the copper wire, because copper is ductile and malleable. We can shape it and we can draw it into a thin wire, and it conducts electricity, and it has a high melting point. So all of these things make copper very, very useful. In fact, copper is one of the most like hottest commodities. They're actually like they trade copper futures, like people have the ability to buy future copper like on the stock market, and it's actually like more valuable, maybe not more valuable, but it's more sought out than things like gold or silver, just because it is so useful. Okay. And then these three specific elements here, iron, cobalt, and nickel, they are ferromagnetic. So those are the three metals that you most likely will see if you have something that's a magnet. Iron's the most common, but then cobalt and nickel are as well. So not all of these metals are magnetic. So a lot of people think that all metals are magnetic, and that's not true. And so that's one way you can tell, what is in something, because if it's attracted to a magnet, it's probably going to have one of these three metals in it: iron, copper, or iron, cobalt, or nickel. Okay. Some of their chemical properties, they form compounds with more than one oxidation number. And so we're going to get more into that next week because we're going to talk briefly about it today, but we're going to focus more on the multiple oxidation numbers because they're going to lose they can lose different amounts of electrons just depending on the situation. They all form positive ions because they're all metals, so they all lose electrons, okay? And then next week, we're going to talk more about how they form these colored compounds. So when these transition metals are in chemical bonds and making compounds, their ionic compounds that they make are usually very bright colors. So there's some that are like blue, yellow, pink, green, orange. I mean, they make all kinds of different colors. And so it depends. And usually the color is an indicator or a clue as to what the charge is going to be, since we know they have multiple charges or multiple oxidation numbers, okay? And then another thing that we will get more into next week is they can act as catalysts. Catalysts are substances that speed up a chemical reaction. They make it go faster. And so a lot of times we can use some of these transition elements as catalysts. So they're not part of the chemical reaction, but for some reason, when you add this substance into the mixture where your reaction is happening, it speeds it up and it makes that actual reaction go faster, which is good because obviously, you know, we know that time is money. And so when there are companies like manufacturing companies or like drug companies that are doing things that require chemical reactions to make a product, if they can make it go faster, they're going to do that because that's going to save them time and they're going to probably maximize their profit margin more. All right, so second part is talking about this idea of a complex ion, okay? So complex just means that it's not a simple ion. You know, if we have an ion that's just, you know, like chloride, like, you know, if I have chloride, chloride's really simple. It's just, you know, Cl minus 1, okay? It's just one atom, but it's got a negative charge because it's gained an electron, okay? And then we have our polyatomic ions. Like I could have, let's see, PO4 3 minus, okay? And that one's a little bit more complicated because if I actually draw it out, it's like a phosphorus and it's bonded to 4 oxygens and, you know, it has a charge and all that stuff. So it's a little bit more complicated than just having something like chloride. But what these transition metals or these transition elements do is when you dissolve them in water and make a solution, they form these complex ions when you put them in a solution, meaning you dissolve them in water or you can dissolve them in something else that's not just water. It could be a solution that has another chemical in it you're dissolving it in. And so a complex ion, it has sort of some different parts to it. So it has a central metal ion. So in this one, here's my metal ion. In this picture, it's iron, okay? And then the central metal ion, it is bonded to these things we call ligands. Sometimes you might hear them, people pronounce them ligands, but ligands is, I believe, technically the correct pronunciation. But it's kind of like Caribbean. You know, you'll hear people say it the other way. But ligand is the correct, technically correct pronunciation. And the ligands in this picture are all of these water molecules, okay? So the ligands are going to be the things that are around the outside bonded to your central metal ion, okay? And then this picture is showing us an example one. This is hexa aqua iron 3 ion, okay? So they have kind of weird names, but the hexa in this case, hexa is because it's bonded to, there's 6 water molecules here, so that's why it's got a hexa. Aqua because they're water, so aqua is kind of like aqueous, like water. And then iron because iron is the central metal ion, and then it's 3, Roman numeral 3, because it has a 3+ charge. So the name looks kind of weird, but all the parts of the name make sense when you break it down, okay? And so this is how the formula for it would be written. So the metals first, and then notice that they have water in parentheses with a 6 after it. So you're not going to have to write the formula for water 6 times, okay? And then the whole thing is in brackets, and then the charge is outside of the brackets. So if you write the formula condensed, you do it like this. If you actually draw out the structure with showing the individual water molecules and how they're bonding, then you draw this. But either way, you always put the whole entire thing in brackets, and then the charge goes outside the brackets up in that top right corner, okay? And so one thing I want to point out is that when when the ligands bond to the metal ion in the center, they bond by a specific type of bond, and it's called a coordinate covalent bond. Now, we will learn more about this when we get to topic 4, because topic 4 is bonding, and we will learn in detail what a coordinate covalent bond is. But for today, just so that we have a basic idea, okay, a regular covalent bond, because we've learned about covalent bonds last year in 10th grade chemistry. So a regular covalent bond is like, let's say I have hydrogen, and hydrogen has 1 valence electron, and I have chlorine, and chlorine has 7 valence electrons. So what happens is if I have 2 nonmetals like this, they each have 1 single electron, so they will share these electrons. And then when they form a bond like this, okay, this bond between them, that's a covalent bond because they are sharing a pair of electrons, okay? What makes something a coordinate covalent bond is that the pair of electrons being shared in the bond both come from one of the substances, one of the things that are bonding. And so the water molecules, the ligands, are always going to be the ones that are going to have an extra pair of electrons to form that coordinate covalent bond. So what happens is in this case, the water, it's using one of its pairs of electrons to bond to the iron. So the iron is not contributing any electrons. Both of the electrons in the bond are coming from the water, okay, or in general from the ligand, okay. And so the next couple part down here, there's this term called the coordination number. The coordination number is the number of coordinate covalent bonds between the ligand and the central metal ion. So on this picture, if I look, there's 1, 2, 3, 4, 5, 6. So on this one, it says the coordination number is 6, as there are 6 coordinate covalent bonds between the ligands and the central metal ion, okay? Now, one thing it's going to ask you is to use the coordination number, or determine the coordination number, and use that to figure out the shape, okay? Now, the shape, also, this is going to be something that we're going to get more into in topic 4, okay? But you did learn basic shapes last year, so you learned things like linear and tetrahedral and trigonal, planar and trigonal pyramidal. You did not learn the ones that go up to like 5 and 6 bonds, okay? So for example, okay, this is similar to the one on the, or actually let's do this example up here. This one has a coordination number of 6, okay? And so what that means is that it has 6 bonding domains, 6 bonding areas around it. And that is going to be octahedral. Okay. And we will, and that's OCTAHED, and that's an RAL. Sorry, kind of wrote it a little messy. So anytime there are 6, it's going to be usually octahedral. If it's 4, there could be 2 possibilities. And so really quick, I'm going to switch over to topic 4 notes just to kind of show you. Okay. So if you have, this goes back to bonding. So we learned kind of the basics of this last year, and we will go over it and extend it when we get to topic 4. But if you have something that is 4, that's generally going to be tetrahedral. Okay. There is another one that has 4. If it has 2, it can be bent, or if I come down here, it can be linear. Okay. The ones that have more than 4, they are, let me go to this one. Okay. All right. So the ones that have 4, so here's one that's got 4 bonding domains, but it's got 2 non-bonding. So the ones with 4 can also be square planar. And so for right now, we're just going to talk about the basics, and I'm going to kind of guide you through doing that practice question today, because this will definitely make more sense when we get to topic 4 and we've recovered all these structures. But if you have 5 bonding domains, like one of the options is it's square pyramidal. Here's the one with 6 that I mentioned. So if it's 6 bonding domains, that's octahedral. Okay. And so the structure looks like this. And if you look, this looks really similar to that complex ion. There's one thing in the center and there's 6 things bonded around to it. Okay. So if I switch back over here to our topic 3, I can see that, like this looks really similar to that. It's got 6 things surrounding a central atom. And so this one would have a coordination number of 6, and it's going to be octahedral. This one's only got 4. I can see 4 things connected, and it doesn't look like there's any extra like lone pairs, so it's just 4, and then so this one will be tetrahedral. Okay. And then this one, we have 2 things connected. So this one most likely will be linear because of that. All right. Okay, last section for today. So we're going to talk about specifically about the ligands. Okay, those are the things that are surrounding that central metal ion to form the coordinate covalent bonds. So these are the most common ones, and it would probably benefit you to kind of memorize them or to make sure that you're aware of them. So water is the most common, cyanide, the cyanide ion, the chloride ion, ammonia, and then carbon monoxide. What all of these things have in common, even though some of them have a negative charge, some of them are neutral, what they all have in common is that if I draw out their Lewis structure, I'm going to draw water. So water has these 2 pairs of electrons on the central atom. So it has a pair here and it has a pair here. Okay. Cyanide, if I draw cyanide, it's a carbon, it's triple bonded to a nitrogen, and then the carbon has a pair on it, and then it's got a negative charge. So it also has an extra lone pair here. Chloride has chloride is Cl, but because it's Cl minus, it has 4 complete pairs of electrons. So it has lots of pairs of electrons that it could give away. Ammonia, NH3, but the N has a pair of electrons up on top. Okay. And then carbon monoxide, it looks similar to the carbon or the cyanide. It's carbon and it's triple bonded to oxygen, and then the carbon has a pair on it. Okay. So what all of these things have in common is when we draw out their structures, their Lewis dot structures, I can see that all of them have these lone pairs of electrons that they could use to bond to something. And so that's what makes something able to be a ligand, because they use their lone pairs of electrons to form the coordinate covalent bonds. So like, for example, chlorine could use this pair and it could bond to a central metal ion and create a coordinate covalent bond. Okay. Water could use one of its, nitrogen could use this one, or ammonia could use that one. Not cyanide and carbon monoxide can use this one. And so all of them, that's what they have in common. They all have the ability to give away one of their pairs of electrons and use it to connect and make a coordinate covalent bond. Okay. All right, so there's a special category of ligands. They're called polydentate ligands. So poly meaning many, okay? And so a polydentate ligand is a special species, and it has more than one pair of a lone pair of electrons to form a coordinate covalent bond. And so the most common example is this substance called EDTA, and EDTA is just the sort of shortened version of its name because it's a really long name. So EDTA with a 4- charge is a really common example, okay? And it has 6 lone pairs of electrons, so it's a hexadentate ligand. So poly is kind of the general term, polydentate, but then if you know the exact number, you can kind of use that prefix. So this one would be a hexadentate ligand. And if you look, it says that the EDTA4 occupies all of the octahedral sites. So in this picture, okay, the M is representing my metal. Okay, so they're just using an M as sort of a general metal symbol. Okay, and then if you notice, it's all connected. So it does have 6 coordinate covalent bonds, 4 of them to these oxygens, 2 to these nitrogens. Okay, and so it's within this whole compound. So all of them are coming from this one compound to the metal ion. And so it says it grips the central metal ion kind of like a 6-pronged claw. So it's kind of like it's all 6 of them. I only got 5 fingers, but y'all can imagine I got a 6th one. And it's kind of like they're all kind of coming in towards that metal ion to kind of like grip onto it. So it's kind of like those games or those little machines, you know, if you go to like Chuck E. Cheese or something, or like a restaurant, and they have those things where you can put in like a quarter or 50 cents or whatever, and you can try to grab like the stuffed animal. So it's kind of like that. They're all kind of coming in, they're grabbing and holding on to that metal ion in the center. And that grip or the ability to do that 6-prong call, it's called a chelate. And so the reason that this is so common is because they use this in a lot of food additives or in a lot of foods because it is a food additive. And so they remove metal ions from the solutions. And then that inhibits certain reactions. And so they can add this to foods to help like preserve them, to keep them fresher longer, and also to make them, you know, safer because they're going to remove metals and things from their solutions.